Hello friends, let us now learn some important points about higher absorption. In the last class, we have learned the ways to increase the screen speed, that is thicker phosphor layer and higher conversion efficiency phosphors. So in this lecture, we will learn about the higher absorption phosphors. So in the higher absorption phosphors, first, the fraction of the X-ray beam which is absorbed by a pair of par speed calcium tungstate screens is around 20%. The fraction of X-ray absorption by a par speed calcium tungstate screens is 20%, whereas high speed calcium tungstate screen is 40%, whereas rare earth screens is around 60%. So the X-ray absorption increases from calcium tungstate to rare earth screens. So this increased absorption in the faster calcium tungstate screens is because of thicker screen used, whereas increased absorption in the rare earth screens is due to the improvement in the absorption characteristics of the phosphor. It is due to improvement in absorption characteristics of phosphor. So at diagnostic X-ray energies, the absorption of X-rays is entirely by photoelectric effect in a higher atomic number elements of phosphor. So this photoelectric effect will result in will occur maximum at or just above the Kiesel binding energy. So the photoelectric effect most likely occurs when the X-ray photon energy and the binding energy of the ejected Kiesel electron are almost the same, and that is maximum. So the photoelectric effect occurs maximum when the X-ray photon energy is at or just above the Kiesel binding energy. So a phosphor with a higher atomic number would have a higher absorption. If you see, the atomic number of tungsten is 74 and the atomic number of lead is 82. So both of these are almost at the end of the periodic table, and the potential of this type of improvement is limited. So it is interesting to note that the improvement in the input phosphor of image intensifier screens has evolved from zinc sulfide to cesium iodide. Actually now we use rare earth elements with atomic numbers less than tungsten. So each of the phosphors used in new fast screens, new intensifying screens or rare earth screens have atomic number lesser than that of atomic number of tungsten. So if you take the element and the atomic number and Kiesel binding energy, yttrium has an atomic number of 39 and Kiesel binding energy of 17.5, barium atomic number of 54 and Kiesel binding energy of 37.4, lanthanum has atomic number 57 and Kiesel binding energy of 38.9, gadolinium has an atomic number of 64 and the Kiesel binding energy of 50.2. The tungsten atomic number 74 and Kiesel binding energy of 69.5. So all these rare earth elements have atomic numbers less than that of tungsten, and similarly the Kiesel binding energies is also less than that of the tungsten. So let us draw some graphs which tell us more. So this is the graph showing approximate X-ray absorption as a function of X-ray photon energy and the relative screen absorption of phosphor. So here this graph or diagram will approximate the X-ray absorption curve of calcium tungstate screen mainly. So notice that the screen is less absorbing as the radiation energy increases until 70 kilo electron volts. The absorption or the relative screen absorption of calcium tungsten decreases up to 70 kilo electron volts. This 69.5 kilo electron volts is the Kiesel binding energy. Just after the Kiesel binding energy, okay, just at or above the Kiesel binding energy, that is above 70 kilo electron volts, the absorption of the calcium tungstate is the highest. So this is the Kh of tungsten, that is less, so the calcium tungstate is less absorbing as the radiation energy increases until 70 kilo electron volt, that is the KH. At KH or 70 kilo electron volt, the calcium tungstate shows maximum absorption. So next we will superimpose the same with gadolinium. So this is a comparison of approximate X-ray absorption as a function of X-ray photon energy for calcium tungstate and gadolinium. So this is for calcium tungstate where KH is at 70 kilo 69.5 or 70 kilo electron volt. So if you take gadolinium has KH of 50.2 kilo electron volts. So the if you see the absorption of this gadolinium, the absorption of the X-rays by this gadolinium will decrease up to the K-shell binding energy, which is 50.2 kilo electron volts, and after 50.2 kilo electron volts, that is at the KH, the rare earth screen absorbs maximum X-ray photons, and slowly the absorption will again decrease. So this is for the KH of gadolinium, which is at 50.2 kilo electron volts. Up to 50.2 kilo electron volts, absorption is similar to that of tungsten. Whereas at 50.2 kilo electron volt, this rare earth screen will develop 4 or 5-fold advantage when compared to calcium tungstate, because the absorption is maximum. The absorption of this gadolinium is maximum and even more than tungsten, and this absorption will persist up to the 70 kilo electron volt of tungsten. So this is apparent that gadolinium with lower atomic number enjoys this absorption advantage over the tungsten. The absorption advantage is in the range of X-rays between 50 to 70 kilo electron volt, because of the absorption of these 50 to 70 kilo electron volt energy occurs because of the photoelectric absorption. Because of the differences in the photoelectric absorption, which is related to the KH of gadolinium and tungsten, so this 50 to 70 kilo electron volt X-rays are absorbed more by gadolinium when compared to tungsten. The rest of absorption is similar to that of tungsten. So if you say in the diagnostic radiology, large percentage of X-ray beam will have an energy less than 50 kilo electron volts. So if you see in the diagnostic radiology, large percentage of X-rays will have energy less than 50 kilo electron volts. So as a result, though gadolinium can absorb energies between 50 to 70 kilo electron volts, but in our diagnostic radiology, when the X-rays or radiation energy is less than 50 kilo electron volt, so this is not of that useful. This gadolinium advantage is less. So that is why we started using one more phosphor, which is called as lanthanum, is added to the phosphors of some rare earth screens like DuPont and Chronex. So this is the picture showing the lanthanum addition to the previous gadolinium and calcium tungstate screens. So for calcium tungstate, the K shell KH is at 70 kilo electron volt. So maximum absorption occurs at 70 kilo electron volt. Whereas for gadolinium, the KH is 50.2 kilo electron volts. So maximum absorption occurs at 50.2 kilo electron volts for gadolinium oxysulfide. Then now we are going to incorporate one more new element, which is lanthanum with 38.9 kilo electron volt has the KH. So maximum absorption occurs at KH, which is 39.5 kilo electron volt. So this is lanthanum oxybromide. So this lanthanum oxybromide will close, or it absorbs the, because the KH of lanthanum oxybromide is 39 kilo electron volt, it absorbs X-rays between 39 and 50 kilo electron volts, and thus it closes the window between 39 to 50 kilo electron volts, because most of the diagnostic X-rays are below 50 kilo electron volts. So this lanthanum is most useful in diagnostic radiology. So by combining the two rare earth phosphors, that is both gadolinium oxysulfide and lanthanum oxybromide, the Rare earth screens have significant absorption advantage over calcium tungstate in 39 to 70 kilo electron volt range. So we have Chronex Quanta 5, which uses this gadolinium oxysulfide and lanthanum oxybromide. Finally, we have one more group of compounds which are not rare earth elements, but they have properties of rare earth elements like yttrium tantalate. Before that, yttrium oxysulfide we will see. So about yttrium. So this is the picture showing the X-ray absorption of yttrium in comparison with calcium tungstate. So we know the calcium tungstate has an absorption K absorption KH of 70 kilo electron volt, where the absorption is maximum. Whereas if you see the yttrium has a KH of very less, that is around 17.5 kilo electron volt. Because of this lesser KH, very less KH, the maximum absorption occurs at 17.5 kilo electron volt. So calcium tungstate and yttrium oxysulfide will match almost similar from this 17 kilo electron volt to this 70 kilo electron volt. At 70 kilo electron volt, there is KH of tungsten which shows more absorption. So these two phosphors will absorb about same X-ray energy. So both this yttrium oxysulfide and the calcium tungstate will produce same X-ray energy, but that is between 17 to 70 kilo electron volt. But yttrium oxysulfide produces more light photons because of its higher X-ray to light conversion efficiency, which is around 18% when compared to calcium tungstate X-ray absorption efficiency of 5%. So these are the important points of X-ray absorption, higher absorption by phosphors. Thank you.